Good morning, everyone. So I'm very excited and honored to be here today to present the work done by my colleague at Deloitte AI Center of Excellence with collaboration of the National Security Institute at Virginia Tech. So this work titled Enhancing Exfiltration Path Analysis Using Reinforcement Learning is part of a series of studies that explore how reinforcement learning could be used to support red team's efforts in penetration testing. All right. So just an overview of what we'll be discussing today. We'll first provide some background information on penetration testing and reinforcement learning. And since this room is full of cyber experts, I guess we'll be focusing mostly on reinforcement learning. And then we will talk about the general framework that are used throughout that series of studies. And then we will dive deep into a specific use case discussed in this paper, that is data exfiltration, while considering protocol and payloads. And finally, we'll present some experiment results and followed by some discussions on how this could be used to alleviate red team's workflow. Right? So just a simple definition, penetration testing is just a simulated attack on the system to expose security weakness in the network. So there, the main challenge the red teams are facing is, when they're dealing with a large, complicated network, say with more than 1,000 or even more, hosts, it takes a lot of time and effort to figure out, how to conduct the penetration test to get to the target, right? And so we think, reinforcement learning could be used as a potential tool to automate this process. So it's not replacing the original way of doing things. It's just trying to, accelerate this whole process by presenting some, results on a large network faster for the experienced penetration testers to review, so that they can say, oh, this attack path makes sense. I will explore this option right further. And again, because of the time and effort required, usually for the given limit of time, you cannot explore lots of scenarios. You can only focus on one specific thing, for example, crown jewel analysis, right? Or maybe just exfiltration. But it's hard to to simulate all possible attacks an enterprise may face. And then just some basic definition about network, subnet, and then exploits and vulnerabilities. Okay, so let's talk about reinforcement learning. It's a subfield of machine learning, and it focuses on training an agent to optimize its behavior in an environment through interactions. So key things here are, it deals with a sequential decision process. So unlike trying to train a classifier to say this is a cat and that is a dog, this one is more about think about playing a game. So it's about finding a sequence of actions that will lead to success. And another main characteristic of reinforcement learning is that because it requires some interactions with the environment, so it doesn't require explicit label data. The agent itself, through interaction, will generate data for training, will generate experience that will be later used to train the agent to adjust its behavior. And this behavior is characterized by what we call policy. So basically, it's a mapping from states to actions, and the states just represent your current status in the, for example, in penetration testing, what hosts have you compromised, right? And then actions are, what you can do next. You can maybe do another scan at a different host, or do, exploit a different vulnerability at a nearby host. Yeah, and then, with that, the key, concept in reinforcement learning is this reward signal. So it's essential to, define good reward signals to help the agent to achieve its goal. So, intuitively, this could be very simple. For example, when you achieve the goal, you receive a reward of 1 and 0, nothing else. But as you may imagine, that will make the learning super slow because the agent will just try a bunch of different things and maybe for a lot of time until it finally got its first success. So it's super hard. So this is a whole area called reward engineering that deal with that to, just to focus on designing reward functions that can accelerate the training process. And we'll talk more about, the reward signals we use in this, whole series of studies. So the key idea is the agent will learn through interacting. So specifically at each time step, the agent has a certain state, and the agent will take an action. Could be scanning or could be exploit or privilege escalation, and then that will depending on whether that action will be successful or not, that will leave the agent to a new state. And along the way, the agent will receive some reward signals. If the action is success, it might receive a small positive reward, right? If it's a failure, it will probably just pay a penalty. So things in that nature. And then for each step, we will store those kind of transitions, as a tuple. So we have state, action, reward, next state, this kind of tuples, and then those will be used to train the agent. And the agent, depending on how you train the reinforcement learning agent, broadly speaking, there are 3 classes of algorithms. So actually, the one used in this paper is kind of the third one that combines the benefits of the first 2. The first 2 are actor-only methods and critic-only methods. So basically, just whether you are trying to directly learn or approximate the agent's policy, or whether you rely some external like value function that basically tells you how good if I take this action at this state, right? So depending on whether you rely on value function or not, there could be critic or actor-only methods, and the third one is kind of combine the both. Okay, so that's a general overview of reinforcement learning, just to lay down some keywords and so that we won't be confused later on. So how do we use reinforcement learning to conduct this kind of set up this environment and then later to simulate penetration tests? So the overall approach or pipeline can be seen here. So essentially we have some real systems, and then we will first the penetration team will perform some scanning actions with consent of the client. So they will do some, for example, perform some Nmap or NASA scan to get the idea of what hosts are on the system, right? What subnets they belong to, and what kind of services, operating system they're running. And based on those information, we can have this very succinct representation of attack graph. Basically, just it shows all possible states, and from one state by exploiting some vulnerability, you may end up with at a different state, right? So all those kind of basic attack graph, and then with attack graph we can then further utilize something known as CVSS or a common vulnerability scoring system, so that we can get the probability or the reward for each kind of exploit or action. And then we can with that we can have a more and more environment similar to what is required to train a reinforcement learning agent. So formally, the environment for reinforcement learning agent is defined as what we call Markov decision process. So it has states, actions, rewards, and then transition probabilities, right? All that, as you saw on the previous slide. So here, based on the basic, attack graph, we can start to fill in those details. Like there could be multiple exploits to attack a certain target, and they could have different, probability for success, right? And then, so based on all that information, we have a Markov decision process, and that's the environment for the agent to interact with and to learn. And So all this line of work is, well, first it starts with the first paper on modeling cyber terrain. So that's where we kind of put the transition probability and the the reward engineering into this whole model. And then we conducted several case studies. So basically just focus on how this model kind of reinforcement learning environment can be used to simulate different penetration tasks like crown jewel analysis. For example, if you want to get a foothold on the most critical asset of a system, right? That's what we call crown jewel. So how do you get there? And not just the crown jewel itself, but also how to get to the, for example, two-hop network, the neighboring nodes of the crown jewel. So all those can be, you can just train the R agent and give you all the possible passes without any human intervention. And then we also a previous study for this one, the most relevant study is that discovering exfiltration paths. So in that study, we just focus on how to find an exfiltration path from a compromised host to a public facing host where the attackers can then download data to their own devices. And we also talk about exposing surveillance detection routes. So that is more focused on just doing reconnaissance, just to try to figure out what kind of services are running on the system of a network of systems. And then we also talk about discovering command control channels, which kind of combined a lot of use cases before. So it's more like multi-stage attack. So in order to finish this kind of attack, the agent has to infiltrate first to get a foothold on some critical assets, for example, databases, and then it has to establish connection to a command and control server over the internet. And then once the connection is established, it will perform exfiltration tasks. So that's kind of combine all of that. But we did introduce a few more cases to make the model a little bit more realistic in this study, and we will see that just in a bit. So this is how the model will look like for a simple example network. So let's say we have a network with say 26 hosts in 9 subnets, and they have different operating systems and different services. And the green node represents the initial foothold. So the agent may already get a foothold on that 1,0 node that's in subnet 1. And then the goal could be to attack, to infiltrate one of those orange nodes running SQL services. So they're probably available databases. And so that's the general infiltration task. And for exfiltration, it's the reverse. So exfiltration deals with how to get data out. So if the attacker has already gained access of one of those database servers, because they're isolated from the internet, so you cannot easily just download them. They need to find out a way to transfer that data to a public facing node where they can later download or access that data. So so that's just the I guess the point I'm trying to make here is based on the same network, there could be multiple different use scenarios depending on how you define your goal and where you start. In infiltration, you start with a green node, and then you want to get to the orange node. In exfiltration, you start with one of the orange nodes, and you want to transfer data to find a path to the green node, which is connected to the internet. And for the states, based on all those information, we need to know at any given time for the agent, it needs to know each host's address. So it's not necessarily need to know the actual IP address. We will just translate that into its subnet ID and local ID. And then we also need to know the operating systems and the services, processes, all those kind of stuff that are for a specific host. And okay. And also we have some status check. So we need to know how many, or at least what kind of hosts have been compromised, right? So that I can start my next step. So if I already get a foothold on, for example, 7.0 here, then I probably will easily find this 7.3 host. So hopefully that makes sense. And then again, based on the scenario, you can kind of craft a different state information as you go, basically focusing on what you're trying to simulate. If you're trying to simulate the exfiltration with payload, then you probably need to know how much left to exfiltrate. And then we have these actions. Again, two main types of actions are just subnet scanning and exploit. And then based on for this specific use case, exfiltration, you also have the action about upload. And there could be multiple upload actions depending on the size. For example, you could upload 10 megabytes or 100 megabytes at a time. And then to evade firewall detections, we could have some sleep actions, just no operation, for that specific action, just to hide out to evade firewall detection. And then for the reward signals, as I mentioned earlier, we could have some small rewards for achieving sub goals and big bonus reward for completing the full attack. And a key thing I want to mention here is that we introduced, in one of those early papers, we kind of introduced this the defensive cyber terrain. So basically, the idea is that, for each action you saw on the previous slide, it will have some cost or penalty depending on what host it's trying to target. So for some hosts, they're probably highly, defended. For example, a host running SSH is probably more secure than the host running telnet, which transfers data in plain text. So that's the idea we built into this reward signal. And so what's the key? What are the key improvements over previous study? So here we specifically focused on protocol. And again, the previous exfiltration study focused only the path from one host to another. Here we're not just considering the nodes, but also the protocols on those nodes. And we also introduced the payload and then the firewall concept so that it will penalize aggressive uploading or exfiltration behavior. So the agent needs to figure out a way to trick the existing system. And then we perform the experiment on two larger networks. The one is with more than 1,000 hosts, and the results show are actually very good. So let me just quickly go over this one. So the idea of exfiltration with payload is just we are trying to maximize the utilization of a given protocol in its exfiltration path. So basically, as you can see on here as an example, if the whole path relies on the same protocol, that will be preferred over a path, even it might be shorter, but it relies on different protocols. And here is just one example. So you're at A2, you want to exfiltrate to 2.0. So I have two paths. The green path utilizes the same protocol, and so it's preferred, and it's discovered by our agent. So that's what we want. We don't want the expert to sit there and to do this all manual check this his or her own. And for the larger network, we have it's difficult to draw the network with 1,000 hosts. So we just show it will still converge. It actually quite a short period of time. So we can see the rewards gradually increased, and then the number of steps in the episode gradually decreased. So that's just shows this approach is scalable. But as I mentioned, it's hard to draw the actual network, but it can identify the key points in this huge network. Like it will quickly pinpoint, for example, this 2418 hosts. So that will help the security operators to to take a deeper look into that host. All right, so to conclude, we developed this kind of RL approach. Hopefully that will support red team's effort and make their life easier. So yeah, thank you all. I'm happy to entertain any questions you may have.
Wonderful. Let's give a round of applause. All right, so we'll start with some from the audience.
Awesome. Nice talk. Are you seeding the simulator how are you seeding the simulator in terms of how it responds to actions? And the second question is, are you modeling the side effects that happen from any of these actions? So you talked about, sort of defenders being able to see different behaviors. Is that being fed back in any way, shape, or form?
Okay. Thank you for your questions. Both are really great. So yeah, I want to also use this opportunity to talk about the limitation and the strengths of this approach. So right now, as we have seen on this slide, the general approach. So it relies on scanning data. So the limitation is that it's kind of a static. So you go in, you scan the network, and then you just use that data to build an isolated environment. But at the same time, that's also the beauty part of this. So you're not cause any real damages to the real network. So all these are done in an isolated environment that mimics the current setup. So that's so to answer back to your original question, how the defenders will react, right? So these are built into actually the reward function. Like I mentioned, the cyber defensive terrain. So they're not responding real time. It's just we kind of engineer the reward signals to penalize actions that might trigger defensive measures, right? Yeah, and also we have this new paper, introduce this network firewalls that will monitor traffic volume. So if you're uploading a huge volume in a short period of time, then this episode will be over. Will be just to start all over again, and the agent will receive a huge penalty. Yeah. Okay.
Excellent. So yeah, now we'll do one from the Slack here.
Okay.
Did you use a private environment to train this approach? Is it derived from something open source? And what algorithm did you use?
Okay, so the environment is built from scratch. So it's not open source yet. It's just, we built all the states, actions, and, reward signals, and especially the model dynamics. But we do, inherit the commonly used OpenAI GM environment for the simulation. It's just, we inherit that. You have to specify lots of more details. So that's what we do, currently. And the algorithm used is PPO, I'm sorry, proximal policy optimization algorithm. It's one of the state-of-the-art algorithm. It's actually used in, last time I checked this morning, it's used in AWS Deep Racer. They use that algorithm to train, really cool autonomous racing cars. So it's just, one of the algorithm we tried, and it shows the best results.
Excellent. Thank you. Another from the audience? Yes, sir.
Yeah, thank you. Quick question. It seemed that the agent was really deterministic on packet size and protocol switching. Did it take any consideration for encrypted versus not encrypted protocols or tunneling or anything like that?
Oh yeah, great question. So far we're not considering that level of details. It's just to focus on, we think it's already a step further compared with past where we didn't consider protocol at all. So now it's just the user, you have to specify the preferred protocol beforehand, and then we will try to find that path, the path utilizing that specified protocol first. And if not, then we will just try to find out one that maximizes utilization. So we're not considering encrypted unencrypted protocol at the moment, but I think, yeah, definitely we can build that into, it's just one more, preference the agent needs to consider. Yeah. Great.
Excellent. One more from the Slack here. How do you define the probability of transferring between states in the RL method?
Okay, yeah, that's also a great question. So I mentioned the CVSS in the beginning. So for each vulnerability, there is kind of a it has its own set of metrics like risk score, the impact, and then so these are not those numbers, those probabilities are not just some random numbers thrown by say our data scientists or myself. We rely heavily on our cyber SMEs, so we will consult with them, say for this kind of say HTTP exploit, we have several options which are more likely to to be successful. So these probabilities are at the moment they're not like truly empirical based, but it's based on the expert's experience, I would say. Yeah.
Excellent. Great. Well, let's give another round of applause.
Thank you very much.
Excellent talk.